Welcome to another class of ATMO 620. I hope all of you are doing well. I hope you're staying safe and inside. And I hope you're ready for, well, yet another step in the journey in the discovery of cloud microphysics. So last time, if you remember, we talked about the nucleation, the process of nucleation, so the formation of a cloud droplet. And we saw all the different subtleties and various complications associated with it. We talked about homogeneous nucleation and heterogeneous nucleation, and we scribbled some formula for those processes. Now, today we will take one step further and talk about the growth of the droplets. This is the first lecture on this topic. We'll talk about droplet growth by condensation next lecture as well. Okay, so essentially, we formed the droplet, right? And we want it to grow. And we want to see what happens as it grows and when it can actually become a raindrop, right? Because remember, we're following this parcel of air as it goes up. It's condensed, so it's formed cloud droplets. Is it going to form rain? And how is it going to form rain? Okay, so how can cloud droplets grow? Well, we said that when a critical size and radius when a critical radius and a critical saturation ratio are achieved, essentially we have a cloud droplet, right? If you remember last time, curvature effect and the Raoult's law give us a cloud droplet, right? Now, cloud droplets such as this one, cloud droplets such as this one are suspended in a field full of water vapor molecules, right? It's full of water vapor molecules around here. And different water vapor and different liquid droplets, different cloud liquid droplets are going to compete for these different water vapor molecules, right? Compete for water vapor. So it would be complicated if we were to consider all the cloud droplets, all the complicated field of cloud droplets. So let's just assume that our cloud is made of only one cloud droplet, okay? And let's see what happens, right? How can it grow, okay? We are assuming that, first of all, the radius of the droplet is lowercase r, and we will be at a unspecified radius r, capital R. So small case r is the radius of the droplet, which we will assume is perfectly spherical, and we'll go at different distances and see what happens. We will call n of r essentially the concentration of water vapor molecules as a function of distance. We're assuming that the water vapor field is homogeneous in the three spatial dimensions, and so this will depend only on r and not also on azimuthal angles and whatnot. So it's not r theta phi, but it's just n of r, okay? It's not n of r theta phi, it's just n of r, because we're assuming homogeneity in all the dimensions, okay? We're assuming isotropy, I think. I think is a better word than homogeneity. Well, remember when we talked about the Fourier heat equation, right? We said, well, heat essentially propagates as a diffusive process, okay? Well, the concentration of water molecules also can be thought of as, or the behavior of the concentration can be thought of as a diffusive process, okay? And like all diffusive processes, it obeys this simple equation, okay? What this equation is telling us is that wherever there are gradients in the flux of water vapor particles, then there is the tendency to move these particles out of the way. So, for example, if we start with a lot of particles, let's say that this is R, and let's say that this is N of R, and let's say that at some point there's a spike. For whatever reason, there's a lot of particles that are at this particular distance. A diffusive process will be such that at a later time, this curve here will spread out in space. And it will keep spreading until eventually it's flat. Okay, this is how diffusive processes work. You know, it's the same if you put a liquid drop of ink in clean water. It's a bit more complicated, but you could think of it as a diffusive process in a way. And, you know, slowly the ink will propagate out. Epidemics and pandemics can, to some extent, can be considered as diffusive processes. Okay, just to cite an example that is relevant to these days. Well, anyway, so we're assuming that the vapor field satisfies this equation, such that if there is an anomalous concentration of water vapor molecules, they're kind of, with time, they'll kind of diffuse out so as to make it more smoother. Okay, we will also assume that we are in steady state. Okay, so I'm just going to report this equation on the next slide. So dN over dt equals d. This is the gradient of n. Excuse me, not the gradient. That was a bad mistake. I meant the Laplacian of n. Okay, and we will assume that we are at steady state. So this is 0. And therefore, we're just going to say that the Laplacian of n of r is 0. Now, remember that we are considering the droplet, and we are considering the droplet at the center of our universe. Okay, so instead of using x, y, and z, it's a bit more clever to use radial coordinate r, theta, and phi, or however you want to define these angles, right? And so when you go from Cartesian reference frame to spherical coordinates, there are some transformations to do, and in particular, your Laplacian is also going to change. We are assuming that n does not depend on theta and phi, and so the terms in the Laplacian that depend on theta and phi, we're just going to say they're 0, and so we're only left with the radial term of your Laplacian. And the radial term is this guy here, okay? So we're assuming that this term is 0. Now, what does this mean? Well, if this is 0, then this we can just simply put to 0. We don't need. And this says that the derivative with respect to r of this stuff is 0, which means that r squared dN over dr is a constant. And we can call this, I don't know, C2, I think we call it. Okay, excellent. So let's just divide everything by r squared. Okay, so that here simplifies. Excellent. Well, let's take another derivative. Excuse me. Let's take an integral. Let's integrate these two terms. I don't know what's happening. Wait. Okay, sorry. We integrate this, and well, this will be n of r is integral of 1 over r squared. I hope this is something that you can all do. This is minus c2 over r plus some constant that we're going to call c1. Okay, and we have this solution. Okay, so c1 and c2 we have to determine with boundary conditions, and we're just going to say that at infinity, so n infinity is going to be equal to some number, n infinity. And at the surface of the droplet, this is just going to be equal to n of r, okay? With these boundary conditions, you can do the calculation, and this is what we're left with, okay? You can verify that when big R is equals to infinity, all this term goes to 0. And when capital R equals to lowercase r, this is 1. And so this goes away. The n infinities cancel out. Minus gives a plus, and so it's an n of r. Okay. And so this gives us a solution for what the field of water vapor droplets look like as a function of radius as we go further and further away from the droplet. Okay. What happens if n of r equals n at infinity? Well, as you can imagine, n of r and n infinity are equal, so these two cancel out. So this term and the dependency of the radius cancel out, and so n of r is a constant, and it's a constant equal to n of r or n infinity because they're exactly the same. Okay? Excellent. The flux of molecules onto the surface of the droplet, okay? Remember, now it's a flux, and this flux is d. This is the constant that we had in from the diffusion equation. Okay, we call this diffusivity, if you will. This is the flux, okay, of water vapor molecules on the droplet. Okay, excellent. Now this we can also compute it because we know it. The mass increase because of this flux is a very simple calculation, right? So we're turning, we know that each little droplet has a certain mass. We are fluxing droplets on, we are fluxing water vapor molecules on the droplet, and so we're increasing the mass of the droplet, and we're increasing it with a term that is proportional to the flux, okay, the flux at the radius of the droplet times the area, okay? The flux is the amount of stuff that's coming at you over an area, and so if you want to know how much stuff is coming at you, just multiply by the area and multiply by the mass, right? Because n is giving you a concentration, so you have to multiply by the mass of the droplet, okay? Substitute, now we know what n look like, so we can just let me write it again. So n of r equal n infinity minus small case capital n infinity minus n of r. Okay, just take the derivative with respect to r. So dn over dr, this is r squared. The minus cancels out. Okay, n infinity minus n of r. Notice that we're taking the derivative exactly where capital and small case are the same, right? And so we can also rewrite this as 1 over the radius of the droplet. Okay, put it back in. This simplifies with this, and what we end up with is 4 pi r, the radius of the droplet, d, times the difference between the concentration at infinity and the concentration of molecules next to on the surface of the droplet times m0. Okay. We can also rewrite this. In terms of simply the vapor density, which is a bit simple. I just want to check one thing because I don't want to give you a wrong information. Just bear with me. I'm checking on the textbook, which for now I'm using. Okay, so M0 is the mass of one water molecule. Okay, mass of water molecule. Okay. Sorry, I wasn't sure. Okay, well, this is the concentration. This is the mass, and so the density is very quickly computed, right? And so this is how the mass of the droplet increases by diffusion. Notice that what is driving this is the difference in concentration, right? If you had an equal concentration next to the droplet at infinity, you wouldn't have any growth, right? Okay. Also notice that there are thermodynamical effects, and the temperature of the droplet usually is not the same temperature as the environment, and a lot of processes happen to the droplet. One of these is the fact that whenever you have condensation, the droplet releases some latent heat because of this condensation, right? And in a similar way as we compute the growth in mass of the water droplet, we can also compute the heat that is dissipated, essentially, the diffusion of heat away from the droplet. Why, you could ask, can we do this? And why does the equation look like this, which is very similar to the one of mass? Well, because heat propagates, we saw it last time, a few lectures ago, heat is also a diffusive process, right? And so it's not surprising that the two are actually quite similar, okay? So just keep in mind there's something similar whereby the heat is the analogous to the mass, and the concentration of water vapor molecules is now the temperature near the radius or in the environment T. Okay. Now, we can put everything together because we have now by conservation of energy. By conservation of energy, the fact that the droplet has a different temperature with respect to the environment is going to cause a dissipation of heat, okay, by diffusion. Also, every time you're condensing stuff on the droplet, you're releasing latent heat, okay? And the total heat that is either given up or acquired by the droplet is going to change the temperature of the droplet, okay? And so the heat that is given up or taken in by the droplet equals the latent heat that is acquired because of condensation minus the heat that is diffused away, okay? Just, remember the equation where we said that the heat capacity was dq over dt, or, delta Q when we talked about gases equals some constant C, V or P, depending on how you exchange heat, times delta T. Now, with the gas, we could talk about CV or CP, depending on how we exchange heat. With the liquids, it's exactly the same thing. Change in heat will cause a change in temperature, okay? But instead of CV, CP, it will be something like CL delta T, right? And here, instead of the heat capacity, we're also talking about the specific heat capacity, okay, CL. And so we'll also have to multiply by the mass of the liquid, which is the volume times the density of the liquid. Okay, so this is the change or the heat that is exchanged from between the droplet and the environment. This is the latent heat. Okay, L, we know what it is. It's the latent heat of vaporization. dmdt, this we know what it is. dq/dt, we know what it is. And now we say, well, let's assume that we are at a steady state, at some kind of equilibrium where there's no, as much heat is dissipated away as it's gained by condensation. So your droplet is neither heating up or cooling down, okay? In that case, you can go back to the equation for dmdt, the equation for dq/dt, do a little bit of math, and you obtain this relationship. And this is an interesting relationship because it's not quite the ideal gas law. And, for one, we're talking about a droplet here. But it's relating a few interesting parameters. It's relating the density of the vapor at the surface of the droplet and the temperature of, essentially near the droplet. okay, the environment near the droplet, with the properties inside of the volume, the box or the atmosphere, far away from the droplet. So that would be T and rho V. And these are just constant. This is the proportionality constant in the heat equation. This is the proportionality constant in the diffusion equation for N of R, okay, if you remember. And this is simply the latent heat of vaporization. This sometimes we can also suppose it's constant. And so K over LD, they're kind of known. You can measure them in a lab. Rho V and T, these you kind of know, right? Because you can go out and stick a thermometer out in the air and you can measure the density of the air and the temperature. These two, on the other hand, they're not usually known. So rho near the droplet and T near the droplet, they're generally unknown. And so having a relationship like this, which I'm going to clean up so that you can appreciate again a bit better. Now it's giving you a recipe to compute at least to constrain these two, right? It's just one equation with two unknowns, so you're not going to be able to compute both of them, obviously. But already you're putting in a constraint, okay? So in a rho RV TR space, in principle, before you could have been everywhere. Now, because of this equation, you're going to be constrained to be on some kind of line that you can determine. And, that's already quite something. It turns out that you can further constrain the system, right? You can actually find just one point and find the conditions near the droplet because we knew, if you remember, what the vapor pressure was of the field near the droplet, right? That was E prime that we saw in the last lecture. And remember, we said E prime was E star, the saturation vapor pressure, times this stuff, 1 plus B over R minus C over R cube, radius of the droplet. This was the curvature effect due to the surface tension. This was the solvent solute term, and these we can constrain, but also the water vapor field is an ideal gas, and so E prime R equals rho VR times R of the vapor, T of the vapor near the droplet. And so now this gives us another relationship between these two that we can compute. E star of R, this we know because we know, thanks to the Clausius-Clapeyron equation. So now we have two equations for two unknowns and we can solve for rho VR and TR. Now, unfortunately, these equations are a bit complicated. And so, it's not like you can simply write down a closed form like, rho VR equals some function of R and T of R equals some function of, this would be not just R. Let's not be too strict. This would be R, pressure, temperature, whatever. Right, it will not be something simple, but you can always solve this numerically using some kind of a numerical algorithm. Let me just drink. Okay. Excuse me. You don't like numerical method? No problem. I have some approximations that might help you. Okay, let's imagine we have a field with a saturated vapor. Okay, so we're at saturation. Now, we can compute changes in the vapor density, right? We can simply compute them like this. Differentiate rho V divide by rho V, okay? Use a combination of the ideal gas law. Now remember that E equals rho V, RV, T, right? And so rho V, let me do it here so that we know what we're talking about. Rho V is E over RV T, okay? If you want to compute d rho V, this would be because both these two are, they can vary, you have to vary both. And so it would be d rho v varying E times dE plus d rho v over dt times dt. Now, how much is rho v over E? I mean, this, I feel like I'm insulting your intelligence. This is simply, now I'll get it wrong, dE over rho v t, okay? Minus the derivative of this stuff with respect to t. So this will be E RV t squared dt, okay? If you divide everything by rho v, we can write it down here. D rho v over rho v. Now this we multiply by rho vt, so this would be dE over E minus dt over t. Simple. Now we are at saturation, right? So this is at saturation. What does this look like? Well, this looks like something that Clausius-Clapeyron could help you with. And so this is L RV t squared dt minus dt over t. Oh, how nice. You can gather everything as a function of, let me write it here. So this becomes L RV t squared minus 1 over t dt. Oh, okay. So now integrate, and this was d rho over rho. So now integrate. If you integrate, you would get, we can integrate from the droplet here to some point inside of the environment, okay? If you integrate this, you'll get to this formula here, okay? We can do some further simplification. We can assume that the density of the vapor, actually, we can assume it doesn't really change much between the density of the vapor close to the droplet doesn't actually change much as you move away from the droplet. And also we can make this simple assumption that T times TR, which we saw here, we could write simply as T squared, okay? So that when you have a power, when they're multiplied together, you can assume that TR is roughly equal to T. With these substitutions, you get to this formula here, which is a relatively simple formula. And now we take one more step. Remember the equation for dq over dt that contained a t minus tr. So substitute that here, okay? And this gives you, because we assumed that we were at equilibrium, we had that L dq over dt equal dm over dt, right? And dq, excuse me, what did I just say? Times L, yeah? And this we had computed, gave you the formula a few slides before, 4 pi r k tr minus t, right? And so we have tr minus t here. And so we can substitute, this was 4 pi r k tr minus t, right? So we can plug this back in. Notice that you have to flip the sign of t minus tr, and so we flip the sign here, okay? And you can compute it like this. And finally, you know the Kelvin equation for dm dt, which we gave sometimes ago, and this was how you could write it. Assume, as we said, that these two rho vr equals to rho vr at saturation. This was the Kelvin equation in general, right? Not necessarily at saturation. Here we needed saturation because we needed the Clausius-Clapeyron equation. Now for the Kelvin equation, we don't actually need to be at saturation, okay? Here we're just taking the Kelvin equation and dividing by rho VR, both terms, right? And so now we have something that's very similar, okay, between the two. And so the temptation to equate these two is actually pretty strong. And if you do all the calculation, then, which you don't have to do it, but if you do it, you end up with something that looks like this, which is, it does look pretty complicated. And essentially, you'd get to a tendency for the radius of the droplet as a function of essentially the degree of supersaturation over a bunch of terms, okay? So I jumped a few steps here, but again, as usual, you don't have to remember all the derivations. You don't have to, it's not important that you remember all the derivations, just remember final result and more or less how we derived these formula, okay? Now we have a formula here for the diffusional growth of the droplet, right? For the growth of R. And this depends, at the denominator, this depends on two terms, right? Depends on this term here and this term here. This you could think of, notice that Fk here has, Fk here contains, this Kt term here. And so we interpret this is pretty arbitrary, but essentially we interpret this as a function that is due to heat conduction. And this Fd here, now this has the d that was related to the equation for N of R. Okay, so this was something that was related to the field of the vapor. And so this is the term that is associated with vapor diffusion. S minus 1 is the degree of supersaturation, where S is defined as E over E star. Oh, excuse me. E over E star, okay? And so how much, when you're at saturation, S equals to 1, and so the supersaturation is 0. But, when the vapor pressure is greater than the saturation vapor pressure, then you have supersaturation. We have ignored droplets curvature effects and the effect of solution. If you do that, it gets a bit more complicated, but not so much. And in the end, you just end up with a couple of terms here, which again, the curvature lowers the supersaturation, and the solvent increases the supersaturation. Okay. Okay. The last few things I wanted to say. Okay, so notice that these the terms that I gave up here, a lot of these terms contain quantities like L, contain K, they contain D, and we said before these are roughly proportional to they have a weak dependency on environmental conditions. Well, it turns out that we can quantify to some extent. We can quantify this dependency, and K in particular is proportional to what we call dynamic viscosity of air, which we indicate as mu, and D is proportional to what is called as the kinematic viscosity, which is nothing else than the dynamic viscosity divided by the density. And the dynamic viscosity, this can be computed in I would say, empirical formula that was probably determined experimentally, so there's no need to sit down and think about ways to derive this. And so if you really wanted to, kind of integrate this, then you'd have to take into account also these effects due to the dependency of mu from temperature. In general, however, the equation for RdR, which we can also write as dr squared, right, over dt 1 over 2, right? So this equation cannot be integrated analytically but some approximations can always be made to make it a bit more tractable, right? Finally, we can have a look at the solution to the equation. Obviously, the solution is going to be very complicated and not possible to write it down explicitly, right? Because where's the equation? Because you have so much dependency here from various terms, and so it's not going to be possible to integrate it. But we can assume, first of all, that curvature effects and the solvent effects are negligible, and then we can assume that supersaturation, FK, FD, they stay kind of the same, such that the equation for the radius becomes something like, dr over dt, r times dr over dt equals, s minus 1 over fd plus fk. Let's assume that these stay constant enough for the changes that we're considering, right? And this becomes some kind of constant psi. Now, r dr is 1/2 dr squared. That's hopefully, not news to any of you. So this is dr squared over dt plus 1/2. And let's say that the 1/2 is kind of absorbed in the psi, okay? In psi here. And so we can integrate this, and this would give us something like r squared as a function of t will be some constant, which is r squared times 0 plus psi times time. Because psi, we said, it's kind of constant, right? It's kind of linear. And so the radius is now square root of r0 squared plus psi t, which also suggests that the radius as a function of time grows as a square root, which means that its growth slows down as the droplet gets bigger or older. And so as a consequence of this, what did I want to say? As a consequence of this, spectra of droplets become narrow. So if you start with droplets that have different radii, okay, so they're in different positions here, they will very quickly reach a certain stage, and then their differences will become smaller and smaller in time. If you don't believe me, well, let's just take r2 squared. Let's say that 1 and 2 are two particles. r2 squared as a function of t minus r1 squared as a function of t. This would be r20 squared plus psi t minus r1 squared 0 minus psi t. The psi t's simplify, and so this is r2 squared 0 minus r1 squared 0. This is pretty intuitive. Now, divide everything by r2 plus r1 now, and so you'd have that, let me write it at the bottom. r2, actually no, not a great idea. I'll write it here. r2 minus r as a function of t minus r1 as a function of t. This is r2 squared 0 minus r1 squared 0. This is a constant and will remain a constant at every t, divided by r2t plus r1t. These are going to get bigger with time, and these are going to stay the same. And so the difference between the radii are going to get smaller and smaller and smaller. Okay. Notice also that the equation that I give you here, this depends on s minus 1, and it doesn't say anything about the arrow of time or the arrow of the of the phase change. And so this is true for the diffusional growth, but also for the evaporation. So when s is smaller than 1, so when we are in a subsaturated environment, this will be negative, and so this will have a negative tendency, and so r will tend to decrease, okay, which also kind of makes sense. Well, fantastic. And so this also gives us a way to compute, for example, how much droplets evaporate before reaching the ground, because we can make some assumptions on, for example, the dependence of the fall speed of the droplet radius. And we can know, thanks to that equation, we can know, for example, how much it takes for a droplet to evaporate completely, okay? Because, for given environmental conditions, we know dr squared over dt. And so how much do they have to fall, these droplets, before they evaporate completely? Interestingly, and not surprisingly, the distance that they need to fall increases the bigger the particles. And so, for example, already at 0.1 millimeters of droplet of radius, which is pretty small actually, the droplet will have to fall for a kilometer before it evaporates completely. Obviously, smaller droplets will need to fall for less, obviously. But yeah, this is pretty interesting. Okay, this concludes what I wanted to say to you today, and we'll continue next time with more stuff about the droplet growth of droplets by population. As usual, any questions, you just let me know. Call me, email me. Otherwise, I will see you for the next lecture. Thank you very much, and talk to you soon.